Alright, should be live about now and such. So, just going to do the usual routine before we get started. So, just consider this some sort of intro, and there's music, and everybody's happy, or some kind of crap like that. Maybe. Everybody's yeah. happy. So, just gotta finish doing a little bit of chat crap, and then I will be ready to begin the counter argument for the day kind of thing. So I thought I would just start. I'm going to play Professor Dave's 3 laws, Newton's law videos. So they're basic arguments, but they don't really understand any fundamental mechanism, so there's no point in talking about physics laws in any other context than understanding that if there is an elemental universe, that would be the only one that actually has laws, and that all the rest of the universes are just a consequence of those laws. So I figure I'll do the little Sisyphus argument first, and just point out how a very simple explanation points out all the elements you need to explain everything eventually. Yeah, pretty much. Okay, get rid of this, I think. Yeah, there we go. Alright, so the simple argument is there's 2 kinds of forces in the universe, and I would argue you could just imagine them as little Sisyphuses, little boulder pushers. And we're just going to use color because that's convenient. But they obviously have something about them. They have a property that distinguishes them. Now, obviously, I don't think it's red and blue, but there's some property, some form, some shape, some makeup that makes the 2 of them identifiably different. And what's going to identify the difference is the 2 kinds of boulders. So there's red boulders, okay, and there's blue boulders. All right, so you could even imagine that there was 2 kinds of universes, the blue universe and the red universe, and they just slid into each other, and that's when everything got weird. But anyway, so the catch is, so the idea is this force stuff moves the speed of light very fast when it's not pushing a boulder, and obviously it moves much slower when it is pushing a boulder. So that's the fundamental function. That's the thing that causes what we call heat, and that's the thing that occupies energy or force, and therefore makes it possible to have force differentials. It's because a force that was going to get here doesn't get here if it's pushing a boulder at the same time. It's delayed. And so obviously the force coming from the other side will have a huge advantage in terms of ruining the balance. And so it could be understood that it's pretty much that simple, that every time force is occupied by matter, you've changed where the force would be, and you've changed what's going to happen to other things that were sort of relying on that force showing up at the right time. Alright, so the simple rules are that only blue Sisyphuses can push blue boulders, and they only push when there's already one pushing, or 10, and they can just push in the same direction. But if the boulder has a Sisyphus on the other side pushing in the opposing direction, then there's a reflection, and the 2 Sisyphuses, okay, the one pushing from this side, like say if there was 10 of them, the last one would fly off, so the 2 will just reflect. And so you'll reduce the speed of the boulder because you've reflected a Sisyphus, and you get your energy back as a reflection. And so the Sisyphus either sticks and pushes if it's going in the same direction or not moving at all, or it reflects. And the only other thing that happens, it's 2 kinds of force, 2 kinds of matter, and there's just these 3 interactions. And the key interaction is that if a blue Sisyphus, okay, tries to push a red boulder, what happens is this doesn't matter if it's moving or not moving, doesn't make any difference. What it does is it just goes through and it comes out a red Sisyphus. Okay, and the same is true for the red Sisyphuses going into blue boulders. They just change their identity. So with those three simple rules, you can not only define how things move in the universe, but you can also describe things like charge, which is the most elemental of the functions. So it's really not in the three laws, but I mean, it's just this basic idea that the electrons and protons have a character difference where the same force hits them and they behave differently. One is repelled by that force, one is attracted by that force. And the simple idea is if you understand this Sisyphus rule, no blue Sisyphuses going this way, okay, are going to be turned into red Sisyphuses, and then they'll go through the blue and turn back into a blue Sisyphus. And so they can't create any pressure in here. So no reds can get to this side, and no blues can get to this side of this object. So obviously there's no balancing pressure, and the two fly right into each other. Really easy to understand. And the simple repulsion of opposites is likewise easy to understand, that every red Sisyphus that goes in here and every red Sisyphus goes in here turns blue, and that means there's extra Sisyphuses in here pushing them apart. So the likes repel and the dissimilars attract, and it perfectly explains charge. And the argument is these three laws of sticking or pushing, okay, reflecting, and transitioning, or whatever you want to call that, changing, those three rules or laws are really the three laws that govern all the functions in the universe, because it creates charge, which is the origin of the next phase, which is the creation of atoms, which don't really have anything to do with a Bohr model, in the sense that they've misdescribed what the nucleus is in the first place, in the sense of not recognizing that it has these neutrons in it, which are just electrons and protons close together. And technically, when it's in a nucleus, we can't tell how close together it is, so it doesn't mean much to say close together in that context. And it's just an arrangement of the, again, you could just argue that you could create say a helium nucleus by having 4 protons and then the 2 electrons at either end, and the electrons would be repelling each other, the protons would all repel each other, and there would be attraction, so it would just all stick the thing together as a nucleus. So you can start building atoms, and so you're off to the big universe race, because you start clumping this stuff and it starts sticking to each other and sharing electrons and doing all that kind of thing. So that's the beginning of the story, and it just should be understood that in talking about Newton's laws, he didn't really know this little tiny universe existed, or at least he didn't imagine it in this form, let's say. And so his laws are a little vague in the sense that they're not specific enough to detail exactly these concepts of why something moves. And so when he says something moves forever, well, that would be in some universe that doesn't actually exist, because the one that we live in, we know that empty space isn't completely empty. So you know that when you do throw something in space, it might go very, very far, it might retain its speed for a very long time, but it is going to hit little particles of stuff, and every time it hits a little particle of stuff, that little particle is going to fly off with some of its momentum, and so slowly over time it's going to slow down. So it's not really a law, because in the real universe it has to deal with the fact that it's in a field of force also. And so I guess, I mean, I've already hit the drag subject, but I guess I could just throw this in to make it, well, I'll wait. Yeah, I'll wait. Yeah, I'll wait. Alright, so I believe it's play the first video and such. So this is real basic stuff. You can't get much wrong, but I'm sure he's, once he gets to the second law, he's going to get a hell of a lot wrong, because he's going to pretend the second law was Leibniz's law and not Newton's law. I mean, Newton wrote it, not Leibniz. Okay. And Newton made it really clear what he meant by it, and they just keep, I mean, you can only call it lying, really. They keep lying about what Newton said.
In Newton's Principia, he describes 3 laws of motion, and the first of these 3 was revolutionary.
So I don't know, this is that's just rhetoric, right? Because a lot of people already knew this would be the logical conclusion. I mean, Galileo had already speculated about this kind of stuff. So, for 100 years they'd already been talking about it pretty extensively. That the idea of there might be something in space. In here we have this atmosphere, and so Galileo already knew the atmosphere was a problem.
It can be summarized as follows. An object at rest will remain at rest, and an object in motion will remain in motion, unless acted upon by some external force.
Net force, it says, actually, in what he wrote. And I don't know if this is actually what he wrote in terms of saying net force. I think he just said a force. But regardless, they play whatever games they can play. So the idea is the force is in whatever form, right? Is the force in the form of the stuff moving the speed of light, or is the force in the form of something carrying Sisyphuses? So you're just basically saying, yes, it's the force ultimately that does all the moving in the universe. The Sisyphus is the only thing that move. The boulders don't move unless they're being pushed. So the only thing that carries the capacity to affect something in terms of changing what it's doing, what a boulder's doing, are the Sisyphuses. So obviously they're just basically saying the boulders aren't going to move till a Sisyphus hits them, and they're going to move exactly as by these simple rules. They're either going to absorb energy, reflect energy, or they're going to do this other thing that doesn't matter in terms of transitioning a Sisyphus. All right, continuing.
The first part seems to make sense, since motionless objects typically don't just start moving.
So typically, and in all cases, you could argue, they don't. So it's sort of a reliable statement that you can't just make things move. Now, their theory of gravity says, yes, you can. You can use a non-force bent geodesic and somehow cause something to move. So there's no Sisyphuses, but we're supposed to believe the boulders get pushed. That's a problem. So I would argue if you have some kind of elemental mechanics for motion, that you'd have to account for it. You can't just say something acquires motion without saying, well, where did it come from? And that's the whole Descartes thing. So they sort of just ignore the previous statements, made before Newton by Descartes, sort of defining conservation of energy by simply saying there's a certain amount of motion in the universe and you don't need to add any more. The motion that's already in the universe is more than enough to keep the whole thing moving forever, because the motion just transfers between one object and another object. It just, things bang into each other and exchange their Sisyphuses. But you can't make more Sisyphuses and you can't destroy Sisyphuses, so you're stuck with the same amount of motion in the universe, and it's just a matter of how much of it's occupied pushing boulders and how much of it's flying through space freely.
But the second part contradicts much of our everyday experience.
All right, so it really
When you
doesn't.
throw a ball, it doesn't keep moving forever.
So
It eventually stops.
We know the context of that everyday experience would probably be broken a long time before you're even in, I don't know what grade you'd have to be in or what age you would have to be in before you find out about what friction is, and that both the atmosphere is just another kind of pond you're swimming in. So it's much thinner water, but it's still waterish. It's still a fluid that you're moving through, and that it's going to absorb your energy.
for a wheelbarrow to roll, or for your car to move, or for a plane to stay in the air, a constant force must be applied. So where did Newton come up with this stuff?
So the way he came up with this stuff is the whole thing of thinking about space and the fact that things are orbiting and understanding that they don't slow down, they don't stop. So obviously they're not affected by friction. So he just imagined the world out there that isn't encumbered by an atmosphere. And again, they already knew some of this stuff because they climbed mountains and they realized the atmosphere is thinner and all that kind of stuff. So it wasn't like they were completely ignorant.
To understand Newton's first law of motion, we have to understand all of the forces that act on a body in motion.
Right, and we know the argument can be made is that all the forces are really all the same thing. And because it's in a different subtle form, they decide to call it something completely different. So, a photon could just be bits of force, sificuses at a distance. That's the simple explanation. It's just a pattern. And obviously, if I have electrons and protons and they're radiating, the proton's radiating only red sificuses. That's the only thing that can come out of a proton is the red ones, because all the blue ones turn into red ones, and all the red ones that leave are just reflections, and so all it can radiate is red. Can't radiate any other. And the blues, the electrons are doing the same thing. They're just radiating blue sificuses. So obviously, if I put a bunch of these red and blue things in the environment, you're going to be able to see patterns. It's just a fact. I put a red one pretty far away, and then I put a blue one closer, all kinds of different relationships to that, and how much that affects you, and how much it pushes you versus attracting you, So, it all makes perfect sense to me.
Our planet is a complicated system, and when we move around in our atmosphere, we experience things like wind resistance and other forms of friction.
So you wouldn't bother saying wind resistance, right? You'd just say atmospheric resistance, or you'd say air pressure or something to indicate you don't need it to be windy. It's just the fact that there is stuff you're going to hit, and when you hit it, your motion is injected into it. You give it your motion, and you lose the motion when you give somebody else your motion.
Which is a force that resists motion.
All right, so it really isn't a force. It's a force carrier. It's capable of carrying your force away. It's capable of collecting. It's boulders, frankly. So it's that simple. It's boulders. And when you bump into other boulders, there's a high likelihood that those boulders will move away with some of your sificuses.
This is what slows us down, requiring the application of constant.
All right, so it slows us down, but the simple absolute fact is it slows us down because it takes our force. We're carrying force when we're moving, and we lose it. So it's just like it's perfectly sensible to think of this as currency. Think of the sificuses as dollar bills, and you're just exchanging the currency. Perfectly sensible. Perfectly reasonable.
Force to keep moving. But think of something like a skating rink.
Ah, very good. So this brings up the whole subject of their understanding of gravity and distance and time. And the simple argument is if the ice is thin, you can travel across it, okay, without falling through if you just move fast enough. Because the faster you move, the less absolute pressure you'll be putting on every square inch of the ice. And the slower you move, the more absolute pressure you'll be applying to the ice, because it's a time-dependent force. And it actually takes time for you to acquire the force. You have to be in it the full second to get the 9.8. You're in less than a second, you won't get the 9.8. So the simple argument is that, yes, how much force you'll be applying depends on how long you're in the force.
The ice is very slippery. It is a surface with very little friction.
All right, so this is, again, a little bit sloppy in terms of talking about what makes something frictionless. And that's basically an argument about smoothness and how lubricants just fill in the irregularities so you can slide across a surface because there's less irregularities. But it doesn't deal with the real pressure argument, which is you're always applying gravity, and there's no way to evade the fact that you will be applying a force onto the surface. The lubricants just allow you to travel faster, which allows you to defeat the gravity because you move faster.
If you gently push a hockey puck, it will glide rather far, much farther than if you pushed it on a table or on the ground. But there is still some friction, so it eventually does stop.
So it's just the fact that gravity's pushing it into the surface, and you can't, every time you have contact with a surface, you're going to be losing your momentum to the surface because you're hitting and contacting and banging into other Sisyphus boulders.
Now imagine, as Galileo and Newton did, that there is a surface that is completely free of friction.
Right, so that's Galileo did do that, so he made these arguments. So it wasn't like this was that miraculous when you figure that 70 or 60 years before, Galileo had already talked about it.
If you push the hockey puck on this surface, whatever velocity it has when it leaves the stick would be retained indefinitely, and it would glide forever, unless...
Right, so again, we all believe that to some extent, but again, there's just a practical fact that the universe, as much as the empty space looks completely empty, we know it's not completely empty. So you will hit pieces of crap, dust, hydrogen atoms, things, and they will take your energy.
Unless some other force were to act upon it. This is the kind of motion that can be seen in the vacuum of space. Stars and planets and asteroids and satellites, these objects have roughly constant velocity, and they never stop moving.
So it's really not true that they never stop moving. So again, it just takes a long time, depending on how much crap is in their much thinner atmosphere. So they're in a, we're much thinner than water in the air, and then you just go a million times thinner, and yeah, it's a lot easier to move. Without sharing your energy with any of that fluid, but there is always something. All orbits degrade.
As it happens, most of the universe is in space, and very little of it is on Earth.
So on Earth doesn't mean much. The real universe is the empty space, and the real matter in the real universe is just these little boulders, just electrons and protons. That's all there are, just these electrons and protons. That's the only matter that's really matter. That's elemental matter. It's the only stuff obeying the rules.
So we should consider motion in space, where there is no friction and no wind resistance.
Right, and if you consider that, then your whole F equals ma thing goes, and your distance thing goes in the garbage, because something going twice as fast will travel twice as far. So, and so I start doing experiments in space, and all of a sudden kinetic energy is going to be awful hard to find where it ever is relevant, where it ever does anything. Because Newton's third law basically says all you can do is exchange momentum. You can't exchange kinetic energy.
To be normal motion. It is motion within Earth's atmosphere that is the special case, where objects are subjected to a variety of variables.
Well, you should just say they're subjected to the fact that they're hitting matter. And they're going to, through those collisions, they're going to end up sharing their motion and diluting it into the environment. It's going to be taken from them. So again, friction isn't a force, an opposing force. It just happens to be that it's something that can absorb energy, period.
This is why a car needs an engine that is always running, because there is resistance from the atmosphere and friction.
All right, so we know the resistance from the atmosphere is a small part of the problem. The big part of the problem is the car is really heavy and it's pushing into the ground, and it's going to move the ground. It's going to break pieces off. It's going to do lots of contact with the ground that's going to degrade its efficiency. But obviously the faster it can go, the less contact it has with the ground, and the less it will lose its momentum. So it loses momentum. I mean, this is the cliche argument I've been making all this, for these years, is that, you roll something on a surface and you think it goes half the velocity at half the distance, but you're wrong. It doesn't. It slows down. As it slows down, the friction changes. So the friction increases as the velocity decreases. And so it's 3/4 of the way down the track is where you'll find yourself. Let's see, I could move this. Yeah, I have to move this. Yeah, I have a little drawing space then. So obviously, the idea is if you roll something on a surface, it doesn't go half its velocity at half the distance. It goes half its velocity 3/4 of the distance. Because the faster it's going, the less contact per inch, the less it's losing per inch. And the slower it goes, the more weight it's applying to the surface, the more contact, the more friction. So the friction is variable, and it extracts your energy with a different efficiency, or however you want to describe it, depending on your velocity.
With the road. But a spaceship can just accelerate to a certain velocity and then turn.
So we know that the acceleration, that flame that he's showing on a spaceship, none of the kinetic energy of that flame goes into the rocket. So the only part of the energy, so you used, the theory is if the flame has 250,000 joules of energy, that somehow you must have produced 250 joules worth of fuel to do it. Yet, you're only going to get the momentum in the ship. So, I mean, there's a gigantic inefficiency somehow. That doesn't make any sense. Why is the spaceship only going to get the 50 joules of momentum instead of the 250,000 joules of kinetic energy? And when we're talking about very small particles, you have a differential that can be those extremes. It's like the bullet and the recoiling gun. The bullet has 2,000 joules, let's say. The recoiling gun has 2. How do you make any sense out of that? You can't make any sense out of it. It can't happen. So obviously, the only force and the only joules that the flame coming out of the back of the rocket had was its momentum. And it did the third law thing. If you're going to give away this way, you're going to be stuck with a lot of that way.
The engine off, and it will cruise at that final velocity without end.
So it does have an end. It doesn't. You can know it can't be forever. It could even hit a big rock, somewhere. But yes, it'll take a while.
The capacity of an object to resist changes in motion is called its inertia.
So again, there's no resistance to motion. So they keep using this concept that somehow things resist being moved, when all the argument is no, you have to throw a siphicus at them. You have to point a siphicus at the boulder, or it's not going to move. But the boulder is perfectly happy to move if you give it energy to move. And the catch is, though, is you have to give it enough energy to move the whole object. So when it's an atom and a bunch of molecules stuck to each other, if you only put in one siphicus, the one siphicus can't move all those boulders. So there's no practical way it can absorb the energy because you haven't provided enough energy. It can't spread it on that big a piece of bread. So there's no hope that the energy could move the object.
This must be applied to get an object moving, and again to slow it down to a stop. Only motion with constant velocity including zero velocity, requires no application of force.
So it required an application to initiate its motion. So again, yes, once it has Sisyphuses pushing boulders, it doesn't need more Sisyphuses to keep moving. It already has them. But once it interacts with something else and starts losing them, it's lost them. And so there's no third law, equal and opposite reaction. There's just the action of you giving away your currency. You have $10 in that direction, and you can give 5 of those dollars to something else, and now you only have 5. There isn't some reaction force that took the $5 away from you. You gave them away.
An object will have some amount of inertia that is proportional to its mass.
Right, so there's no inertia. There's just an obligation to give something force for it to carry the force. It can't be a force carrier unless you give it force. But it doesn't in any way resist moving. It's just that if it has more mass, obviously you need enough Sisyphuses to push all the boulders. The same Sisyphus can't push 5 boulders. It can only push 1.
Value measured in kilograms. More massive objects have greater inertia or greater resistance to motion.
So there's no greater resistance. Again, it's just so obvious. You have to put water in the bucket for the bucket to have water in it. What's the big buckets aren't resisting being full. They're just saying, well, yeah, you got to pour a lot of water in maybe to fill the bucket. But there's no resistance.
Think of a tiny sailboat versus a huge...
No, think of a bucket and just say, yeah, it's easy to fill small buckets. It's harder to fill big buckets. So what?
Huge luxury cruise ship. A strong gust of wind is enough to get the sailboat going. And if it hits a rock, it will stop on impact.
So we know whatever stopping means, it'll crush on impact, or all kinds of things will happen, but it's going to share its condition with the rock. And obviously the rock being very dense and very hard, it's not going to be terribly interested in the relationship. And so it's going to do the reflection thing. It's just going to reject the energy and just say, you deal with it. And the boat's going to deal with it by changing shape.
But the cruise ship needs huge engines to accelerate from rest. A lot of force is needed to get it going, and a lot of force is needed to get it to stop. Similarly, it is easy to set a ping pong ball in motion. Just give it...
Yeah, so you're just saying, yes, if you have a lot of Sisyphuses to exchange, then it's going to take you a while to get rid of them all.
A flick. But a bowling ball will need quite a bit more force, and more force to stop as well.
Right. So again, but this is not a miraculous thing to understand, that if you understand the force as a quantity of something, you can understand that big objects need more of the quantity to move the same velocity. So if I want to move the bowling ball the same speed as the ping pong ball, obviously I have to provide a proportional amount per mass of energy. I have to have 3 Sisyphuses per atom, or 3 Sisyphuses per electron, or whatever the argument is. And obviously if I have 1,000,000 electrons versus 500 electrons, I'm going to need a lot more Sisyphuses to get the same speed.
As any bowling pin will tell you. In this way, mass is essentially a quantitative measure of an object's inertia.
So there's just no use for this word inertia. It doesn't mean anything. Mass takes care of it. Big mass needs lots of force to push it. Small mass needs less force to push it. Duh.
As we said, this applies to objects that are already in motion as well. If you get into a car accident, the force of impact will stop the car, but your inertia dictates that your body will tend to continue moving.
Right, if you're not tied to the car, obviously. So all the parts, I could put anything in the car, and if it's not attached to the car and has no sticking obligation, then yeah, it doesn't know there was a collision. How can it know there was a collision if there's no contact it's making? So if there's no contact, it doesn't even know there was a collision. So yeah, it just keeps moving because nothing's forcing it to stop. It isn't interacting with a countering force or a different, a boulder.
And this is why we wear seat belts, because without them, we might continue moving right through the windshield, which wouldn't be very fun.
Well, flying out of the car wouldn't be very fun either, as your example showed, but whatever.
So Newton's first law can be summarized as the law of inertia.
All right, so that's their summary, and there's no law of inertia. There's no meaningful statement here of recognizing that heavy things need more force to move than light things. Duh. I mean, I think they knew that 1,000 years ago or 10,000 years ago. I think they had already figured that out. That it's harder to lift big rocks than it is to lift small rocks. It's just not that complicated. So, as a summary, that's just nonsense.
And it tells us that in absence of a net force, an object will...
It tells us that something needs to be pushed. That's what the whole thing is basically saying. Pushing matters. So if you're pushed, the pushers stay with you until there's some reason for the pushers to leave. And the reason they have to leave is because some other pusher showed up pushing in the opposite direction. And that needs to take place. And if that doesn't take place, yes, once the Sisyphus is pushing a boulder, the only way he can be freed is some other Sisyphus has to apply a counter momentum against his motion.
Preserve its state of motion, whether at rest or moving with constant velocity. We must understand...
So that's not, in my opinion, not the important part. The important part is understanding the idea that there's matter and there's force, and matter carries force. It occupies. Sisyphuses are stuck to it. And so you can exchange force by being directly hit by a speed of light force, or you can exchange force by interacting with something else carrying force.
And what net force means, because there will often be multiple forces operating on an object, and the sum of the vectors representing these forces.
So there's no such thing as the normal force or the frictional force. They're not forces. They're points of contact that should be better understood as like with electricity. You make contact with another conductor. If you make strong contact, you can lose a lot of energy. You make weak contact, you can lose a little bit of your voltage. They're drains, they're sinks. They're objects that can absorb your energy.
Is called the net force. If the net force is not zero, there will be some acceleration.
So acceleration, there's no point even saying the word because it's ultimately just a velocity. So, you keep needing the initial force that causes motion isn't causing an acceleration, it's just causing motion. And then it's the constancy of the force, or even if it's an irregular force, that changes that velocity over time, like adds more or adds less, takes some away, adds some. But it's just adding velocity. There's no such thing as acceleration in any other form than increasing the number of Sisyphuses or decreasing the number of Sisyphuses. It's a quantity. You're either taking it away or you're adding it, but that's all there is. There's no real acceleration.
If the net force is zero, there will be no acceleration.
And so he should say velocity. That's the simple point. You're just going to acquire a velocity. If you absorb the force, then you will move. If you don't absorb it, you won't move.
Now we can move on to the second law of motion. But first, let's check comprehension.
No, we won't bother with that part. No. No, we won't. Okay, let's see. This is a little like the Stickham days. Well, it's not much like that, but whatever. What's the most surprising thing subject physics got wrong in? Well, as I'm sort of illustrating, I mean, if you go to the website, you can see the subjects are right there, and they got every single one of them wrong. So what do you want me to say? The non-existence of the strong force? I mean, the simple conclusion that you just stick an electron between two protons and you can get them very close together. I mean, it's just couldn't be any simpler than that, right? I mean, I got two protons and I want to get them close together. How do I do it? And I could just say I have two south pole magnets. You know, these are, you know, I could just make it two magnets, and I say, you know, and I say, oh, I want to get these two repulsive magnets together. Well, the simple solution, right, is just stick the north magnet right in between, right? So, no problem. I get the two souths very close. And then what happens if I, you know, kick that magnet out very quickly? Well, then I end up with two south magnets that are really close to each other, and they're going to fly apart with a lot of energy. All right, so, you know, because of the rules I just pointed out, all the blue Sisyphuses are going to be flying and turning into red ones, and so they're just going to be a huge amount of pressure is going to build up between the two, because all of one half of the energy in the universe is all of a sudden now turning into a Sisyphus that pushes in opposite directions. So the two things have to move apart. And, you know, so I could say, oh, that's number one. No, that's not really number one. I mean, as I'm arguing, momentum this one seems a pretty big subject. I mean, how do you get much bigger than energy? I mean, energy is the most fundamental physics subject you could really talk about, right? I mean, is there anything to talk about if you're not talking about motion? And motion is energy, right? Mass moving is energy. It's momentum. So, you know, I mean, is there, you know, I mean, I've been over it so many times, but I mean, you know, their law says it takes 25 times the fuel, right, to just go 5 times the velocity. And we know it doesn't happen. And so they took a simple thing, mv, okay, which we know basically means that m, you know, what levers allow you to do, for example, that big M, little v equals little m, big V. That it's momentum exchanges. And so you can exchange your momentum. A big thing, a bowling ball, can give its motion to lots of pins. But if you add up all the mass moving a velocity, if I add up all the MVs, the MV going in is exactly the same as the MV that the pins are now moving. There's no exchange of kinetic energy. The kinetic energy numbers won't match. So, you know, it's, how could they screw up something so, this is so simple. It makes such perfect sense. It's the law of the lever right there in front of you. The pulleys, all this stuff, it's right there. It makes perfect sense. Why break that? You have to say. And especially why break it because somebody says so. And, you know, so, but that is that wrong conclusion. I mean, the reason why they believe in this nonsense is because they can't even get a simple gravitational theory right. So in spite of both Galileo and Newton basically saying it's a time-dependent force, you know, that it's all about, Galileo pointed out, 1, 3, 5, 7, I mean, the odd numbers, the squares, he pointed out all that crap, that it's the square of the time, blah, blah, blah. And, you know, they just paid no attention to what was realized. And so, you know, Leibniz just claims, okay, without any evidence, without saying, oh, I did the experiment and I collected the energy in some specific way. So 4 pounds dropped 1 distance versus 1 pound dropped 4 distances, right? And they're going to tell you, okay, that even though they know it's 9.8 meters per second of velocity over 1 second. It's not any number of seconds, it's just 1 second. If I change the number of seconds, I have to change the 9.8. The ratio has to be over 1 second. It can't be over some other number, then you got to change that number. So we know it's a time-dependent force. You know you only get 2 units because in the first second it does this, and in the second second it's here. Okay, so this is 1 unit of time to do this whole distance. That's 1 second. And this tiny bit of distance, this 1 bit of distance, 4.9 meters in 1 second. And, you know, how can they get this wrong? And then how can they sit there and think about it and say, okay, a 1 mass times 4 distances? It's not a times 4 distances. It only got twice the velocity. It only got 2 units of 9.8. That's so obvious. So it's 1 times 2. How can 1 times 2 equal 4 times 1? And that's what they believe. Their great math is that they actually are going to argue, okay, that it's true that 4 times 1 equals 1 times 2. I mean, obviously it doesn't, but they never tested it. So this misunderstanding of gravity that has something to do with distance, and again, I've made the argument. I mean, how can anybody counter the argument? Let's say this was the Earth, and you're a thing, and you're going to fly by the Earth. You're going to travel this distance in the gravity. The substantial gravity is this little bit here. And so you go really, really fast, you know that, oh yeah, you don't get bent at all because you're only in this gravity for a millisecond. And then you go really, really slow and you know, well, yeah, no, I'm going to crash right into the Earth because I'm in the gravity and I get 9.8 per second, 9.8 per second, 9.8 per second, so I get pushed into the Earth. I mean, it's just so obvious it's about time. It's not about this stupid distance. It's about how long you're in the gravity, not what distance you're traveling. And again, it holds, MGT works in all circumstances. So if I'm a meteor heading for the Earth, right? So I'm a meteor, I already have a velocity of 500 miles an hour, and I'm it's going to be more like 25,000, right? 25,000 miles an hour. And I'm heading for the Earth. Well, obviously I'm going so fast that the Earth's gravity is almost going to be irrelevant because I'm only going to be in it a total of maybe 3 seconds. Any substantial gravity. So at that speed, I'm only going to be in substantial Earth gravity for 3 seconds. So all I'm going to get is, what is that, 18 or something? Let's see, 19.6 plus 9.8 is 27 or whatever, right? So all I'm going to get is an extra 27 miles an hour added to my speed. So I'll go 25,027 miles. I'll get nothing from the gravity. But if I travel that same, 100 miles at 25 miles an hour, well, then the Earth's gravity is going to give me a ton of velocity because it's going to take me a lot longer than 3 seconds. I'm going to be in the gravity for 30 minutes, and I'm going to acquire a lot more velocity. So maybe that's the subject, right? That's where it starts. Their misunderstanding here is what led to the kinetic energy thing. And again, they didn't have any evidence, so they never proved this. And then they did this stupid just dent the surface of clay, with a 1 velocity object and a 2 velocity object. And instead of letting it penetrate, you just dent the surface. And if you just look at a round object, you can see that, well, the deeper it goes, the more it pushes sideways. And the less deep it goes, the more it pushes straight down. And it's kind of obvious that if you push something down, you still have to push it sideways. Just like water waves. The pressure moves through the water in one direction, but it can't push because the pressure increases. So the water ends up going up because there's less pressure up. It's that simple. All right. So, you can go on and on, right? So in every case, so then they made a model of an atom, and they turned it into this insanely silly, I mean, again, this is something, I don't know why if you want to call it intuition, we could argue that I wasn't well educated, especially well educated. I would argue that maybe I climbed some trees, so I knew something about weight and balance and stuff. But I can't give you a specific reason why I innately knew this couldn't possibly be the right answer, but I knew it was the wrong answer. It just can't be true. So they drew this idea of the nucleuses, right? And they said, okay, here's 2 atoms sharing an electron. And this is the crap they drew when I was a kid. This crap, right? And this is after they explained, all right, I already knew. They told me, okay, that, basic rules like, if you go into a gravitational field, you need to slow down. Like in 1969, they landed on the moon. And this is something they pointed out. Well, you got to slow down if you want to get into an orbit around the moon. You can't just go in and pick a vector and you don't have to change your speed. You always have to change your speed to get into an orbit. So how does the electron do that? How can it go from this orbit, like say these two objects are getting closer or moving apart from each other, this speed would have to be constantly readjusted for this orbit to be consistent. So it couldn't possibly be orbiting. It just doesn't make any sense. And then you're saying shared electron. The shared electron is going to all these locations. Why would this atom stay here if the electron it's sharing is way the fuck over here? I mean, it doesn't make any sense. It just seems so fucking obvious. The electron must stay here. It must be in this place. And the two nucleuses are sharing it. That's the only thing that makes any sense. You can't have all this orbiting crap. It's way too complicated. So again, just doesn't make any sense. That's it. Way too complicated, right? They draw the stupid photon as the two fields, blah, blah, blahing. you know, and it's just, you're saying, how does it do any of that? And they don't even tell you how many of these things you need. How long is a photon? You know, they don't even describe any of that stuff. So it doesn't make any sense. How does it know to be this much amplitude or this much amplitude? How does it know to do any of this crap? I mean, it's a silly explanation. What's making it do that? It has muscles? I mean, how does it know I'm doing this? How does it do that? And then if you say, well, the force coming from the sides is doing it. Well, what do you mean? There's a force making it go up and down that's all the way between us and a star that's, a million light years away? Oh, bullshit there is. So, I mean, there's another example. I mean, this just fail. I mean, atoms are not... now they draw it, okay, without the orbitals as just these lumpy things they put in here. But the drawing really is still implying motion, and there isn't any. I mean, there's just jittering. It's just jittering here, and it's jittering this way. It's all jittery, okay? But that's it. And it's only jittering because the universe is not perfectly balanced. And especially not perfectly balanced when there's other matter on either side of you that's constantly changing the balance. Alright, well anyway, so I could do that. I could do the double slit experiment, right? So that's the whole point of these videos. I can show you each one of these subjects and point out how, well, here's the simple answer, and every single time they wanted to force the crazy answer to be right instead of the simple answer. So, like Lesage gravity, it's called mock gravity. You know, the idea that there's a force, a flow, and that matter is just pushed by it. They rejected it because of the drag argument, and I've pointed out that there is no drag argument because you can't change how much force is on one side of you by moving into it sooner. You can't change the fact that it exists, and you can't run away from the force because as soon as you slow down, it catches up and pushes you again. So there is no drag problem. But they didn't pursue a solution to the drag problem. They just took any excuse to run away from the simple answer and instead go with some wooey pull bullshit. You know, that has no source, that doesn't make any sense. I mean, wait a minute, you want me to argue? I looked at, I posted it into Google. I asked Google, why is the Earth melted in the center? And it gives me the dopey answer that science says it's uranium that has a half-life of 10,000 years. So I don't know where's all the new uranium coming from to fuel the Earth's core, and how does it stay a constant temperature when it's half-life decaying at an insanely fast rate compared to the age of the Earth. So if you believe in evolution and geological evidence, the Earth's a damn old thing. And there's no way uranium is what's heating its core. So that's a silly answer. And the other answer is it got bombarded 4 billion years ago with a bunch of asteroids and it's still hot. So even though we can't make a perfect thermos, somehow the Earth is a perfect thermos and it's just held all its old energy inside of it and it hasn't leaked out. I mean, it's a bullshit answer because we know if I put something hot in space, all of its energy is going to leak out. Fact. So I can just go on and on and on, right? Every single subject they have butt fucked it, so to speak. And they've chose to, you know, put it in the wrong hole. Ugh. Okay. Interesting. Yeah, I see how your model of motion, energy, and gravity is better explanation. All right, so let's see what this new person says. Makura. Thanks for your simulation. I think that it's a major contribution to physics. Yeah, well, I'm just saying, the fact that I have explained charge, I mean, it really is the most elemental function. It causes all the other stuff to happen, in a sense, right? It's the interaction between electrons and protons which makes atoms, which makes all the rest of the shit happen. So it's so fundamental. They have zero explanation, nothing. And I'm giving you a simple 2 + 2 + 3 interaction model. I mean, it couldn't get any simpler, really. I mean, it could be 1 + 1 + 2. I mean, you know, maybe, but I don't think anybody can do that. I don't think you could actually make it any simpler and have those three functions happen. You know, the two functions of the same things repelling and the different things attracting. I don't think you can create that much complexity in behavior with any simpler model. So yeah, it's gigantic. You know, it's huge. It's bigger than, okay? I mean, it's a pretty big discovery, frankly, of being able to discover a mathematical, a geometric solution that's that simple. I'm also still willing to contribute money if anyone accepts your challenge. I appreciate all of that, and like I said, I won't take advantage. You know, I'll try to be careful with your money as if it was my own, so to speak, and such. You know, so but yeah, this is what it might take. Yeah, I just hate the idea of paying people for behaving badly. You know, it's like, why should I have to pay scientists to defend their crap? It really shouldn't be something you have to pay them to do. There should be some science group somewhere that's willing to take on the challenges, and there's none. All right, the double slit experiment and the wave function was a step in the wrong direction. Was that what started particle physics to go wacky? Well, I'd argue that a huge part of this is the mv squared part. That made Einstein, that made the mv squared, I mean, you know, the famous equation, energy equals mc squared, you know, did all kinds of things to make a mess, that squared velocity idea. So if you want to say that which one made a bigger mess, I mean, obviously the whole woo of quantum mechanics and the Heisenberg principle and all that horse shit is based on the double slit. So yes, I guess if I'm going to say which mistake was bigger, the misinterpretation of the simple double slit experiment is the bigger error. And it's got more lies in it, frankly. I mean, they have the lie of, you know, saying that 4 pounds dropped 1 foot is the same as 1 pound dropped 4 feet. I mean, it's just they never did the experiment, you know, so it's ridiculous. And to deny that gravity is a time-dependent force when it says right overtly to you 9.8 meters per 1 second. 1 second of time in the force, and you gain 9.8 meters of velocity. It's undeniably a time-dependent force. You can't call it anything other than a time-dependent force. And I can compare it to a stream of paint. I can compare it to a river. I can compare it to the Mississippi River. And I can say, what matters if I'm going to cross the river? How the distance between the two shores, does that matter? Or does it matter how fast I swim across the river? The faster I swim across will decide how far down the river I get pushed. And that's obvious. Speed will decide. Nothing else. And speed is time. All right. Electrons and protons in geometric patterns oscillated by force bits seems more irrational than orbiting electrons. Well, to me, it seems like infinitely more rational. I mean, atoms are really solid, right? And compounds and all these things are really solid. How could they be really solid if they weren't stuck in a kind of rigid geometry? If you could move the electrons that easily and have them all over the place, I mean, the whole thing would turn to a liquid. It would turn to mush. You couldn't have anything called a solid. Okay, Wikipedia seems to push an agenda. Well, obviously I did a whole thing with Wikipedia. They banned me for life merely for suggesting this. I didn't try to post on the Wikipedia page. I didn't even try to make a competing page. I just suggested we should have a conversation about what they're claiming has been proven and what the evidence actually is. If you're going to say something has been established, then you should explain. And they don't explain. They should explain where 1/2 mv squared came from. And it came from a delusional, psychopathic, religious kook. That's where it came from. Who died a nobody because nobody bought it. All right. And it wasn't just because of a couple of cult members who survived past his death who propagandized this crap that this religion got off the ground again. But that's all it was. It's just religious goop. It's not a scientific theory because it's not based on any experimental evidence. He didn't crash cars. He didn't launch rockets. He didn't blow up dynamite. He didn't do anything to demonstrate this kinetic energy thing actually works. So, you know, it's just disgusting that you can't argue any of this foundational physics for which they have no experimental evidence. Again, they haven't even done the simple experiment. Just turn a scale from measuring your weight this way, just turn it this way and bang things into it and see what velocity they have to travel to weigh their weight. How fast do I have to move you for you to weigh your weight horizontally as an impulse? And the fact is, it's the same speed for anything I bang into the scale. Same speed. Elephant, 1 mile an hour. Mouse, 1 mile an hour. That's telling you something. Okay? It's a really interesting fact. Okay? That's what you have to move matter for it to have the weight that we have established as gravitational weight. And it's just about how many atoms you have. Just count the atoms moving at 1 mile an hour, and it tells you what the scale is going to read. You have 1,000 atoms, you weigh 1,000. You have 1 atom, you weigh 1. That kind of thing. It's that obvious, that complete. It's a complete thing. It's all done. You don't need to fix it. They didn't need to fix momentum as an idea. Again, Galileo, Descartes, and Newton all understood it. Quantity of motion, and they all talked about this idea that it's something that just gets transferred from object to object. This wasn't an unknown conversation. And it's just silly to break something that worked perfectly. There wasn't like some example that just, oh, that's just completely ununderstandable. Especially when you understand things like, well, if I take the energy, if I hit you with this pen in this shape, it's going to do less damage to you than if I throw it at you this way. So the same exact momentum, and all I have to do is change how it hits you. And then if you understand that, well, there's another thing I can change the velocity, the time with which the whole contact will take place. And if I make the contact happen in a short enough period of time, I can break atoms. They won't have time to elastically readjust. They won't have time to do all that stuff. And I can actually just split them off, break off pieces, do all that kinds of damage. So yes, it'll do more damage to impose energy quickly, the same momentum over a shorter period of time, but it doesn't mean it's more energy. It just means you applied it in a way that atoms can't handle. But it's the same ability to move mass. You move the same amount of mass, it's just that you moved it in very high velocity in one direction, and so it did more work because it didn't get dispersed as quickly. It's like the friction argument. If I'm going slow through a gel, all the gel sticks to me and my energy disperses into little directions and vectors all over the place. But the faster I go, the less contact I have, the less energy I lose to this stuff going dispersing. So in a sense, my energy is more durable because it gets lost to friction much slower. So that's the advantage of speed. So it can be understood. It's not more energy. It's just applied in a way that the particular thing you're applying it to can't handle. Could force beats be manipulated? No, in a velocity that oscillates protons and electrons. So that doesn't even, it's not a good enough sentence, sorry. Could force bits be manipulated? Well, the force bits are only manipulated in the sense that they either push or they reflect. So there's no other manipulation. So you can't change what they do. They always move the same speed when they're free, and they always add the same pushing power when they're pushing an electron or proton. So those are always consistent. Those are the rules, the very simple rules that govern the universe, and you can't change any of that. In a velocity that oscillates, so the oscillation just comes from the fact that you could obviously imagine a universe with trillions of these little things flying around, and that there's never going to be exactly the same amount of energy coming from one side as the other. At any one moment, there's a little more this way, and then there's a little more that way, so it's like flipping coins. You can flip with your two hands, right? And the numbers of heads and tails is never going to be exact. Well, sometimes it's exactly the same, but most of the time, one side's going to have more tails than the other side has, that kind of thing. Let's see. So really, 1/2 mv squared was the biggest mistake that drove physics on the wrong path. Well, as I just pointed out, probably a bigger mistake was the preposterous interpretation of the double slit experiment. Where would physics be if it didn't make those mistakes? Well, you can understand something like the electron. They measured the weight of an electron by using 1/2 mv squared. So if you can understand that they made this preposterous exaggeration in the energy, which meant that they're not realizing that the electron is actually much heavier than it is, because they had to account for its high velocity or its high energy. And so the electron would have been measured much heavier if they hadn't used the stupid mv squared to measure its velocity. And it in turn measure its kinetic energy. So if they didn't bother measuring the electron's kinetic energy, they would have got its mass at a much higher number. I mean, little things like that. I'm just saying it invades all parts of physics, this kinetic energy nonsense. And so it's broken a lot of other things because it's just not the truth. A proton can't knock down the Empire State Building. I mean, frankly, they basically have a theory that says if protons could actually, speeding protons or helium nucleuses, cosmic rays, if they actually could get to the surface of the Earth, they'd, annihilate the Empire State Building or some kind of nonsense like that. And it's just because they have a silly formula that completely exaggerates how much that proton can exchange. Its momentum is a number like 4. Its kinetic energy, because it's so tiny, is a number like 4 million. So they're saying it has 4 million joules when really it only has 4. It's almost like the bullet example. I mean, frankly, the bullet just doesn't have thousands of joules of energy. It can't move more matter than the recoiling gun can. It can't exchange any more energy than the recoiling gun can in terms of motion of matter. And all of this they could test. Let's understand, Joule made Joule tanks 150 years ago. So, we certainly with our modern technology could do a lot better at making insulated water tanks and just do these simple experiments and see how much something heats the water. And it'll tell you how much, it'll tell you everything you need to know about how the energy has been dispersed between the recoiling gun and the bullet. It'll give you the answer. And the fact is the recoiling gun is going to carry more heat, so it's going to heat the water a little bit more than it should because it's going to have some heat instead of just motion. So I'd say it's not a perfect equal exchange of the explosion, because more of the explosion is going to hit the gun that's going to hit the bullet. The bullet has a very small surface area, just the end of the bullet, and the gun has the up and down parts and all the other parts. So the gun's going to carry more heat. It's going to heat more water. So that's the irony. The gun's going to be shown to have more momentum than the bullet, because heat is momentum. I mean, motion, you could just argue, is heat in one direction. So if I can get heat to all go one way, that's motion. So it's just sort of like the argument with the light bulb. If I can get all the photons to go one way, I have a laser beam, and I can do all kinds of stuff with the laser beam that I can't do with the dispersed light. But it's the same amount of photons. Yeah, it is an interesting question. I mean, obviously most advances in our technology are trial and error. It's not theory. I mean, theory didn't make the CDs, it didn't make the DVDs, it didn't make the laser thing, it really didn't. And if you really look at what happened, even the blue LED is such a good example, because it took 20 years of trial and error. You're just trying to find the right chemical to create the right reaction. And, and you have some theoretical understanding of the piling up of the electrons and this and that and doping the material. But I mean, I'm just saying the theory didn't drive it. What drives innovation is somebody just trying this and trying that and trying some new way to do it, to disperse the heat or to make the object smaller, or to do this or do that. So it's all engineering, and there's not a theoretical path to innovation. It really is it's focusing on a small detail and saying, well, look, this glass gets smudgy. What can I do with it? Well, I could put a film on it, okay, and I can create a film that scratches, but you don't see the scratches because they're self-healing or some kind of it's just engineering. It's not theory. I mean, I shouldn't say it's not. There's some of it's theory. I just mean it isn't deep theory. Okay, it's theory like what goes up comes down. I mean, it's really simple theory, and then just applying it over and over again based on that principle. It's like the Wright brothers didn't know much about buoyancy, but they did figure out how to make a plane fly. So I can't say we'd have a hugely advanced technical society if they had done this right. But what they would have had is a huge amount of money, because they wouldn't have wasted billions and billions of dollars on particle accelerators and LIGO and neutrino experiments and all this other horse shit. So they'd have a ton of money to cure malaria or do something useful that they've wasted on these silly, nonsensical, fake physics things. Gilbert, I'm really not a social person. I really don't do, hi, how are you? It's so special to see you. It's really not, it's not my agenda. Not that you're not a nice person, all that kind of crap. It's just I'm sort of focused, and I really just don't, I'm not doing this for social interaction. I am doing this to make physics arguments and have them understood. Yeah, well, it is true that you can't make too many mistakes in this baking of this pie. But it's true for baking a pie, right? You can't make too many mistakes. And physics has just made mistakes all over the place. And the whole thing is an undercooked pile of slop. And you can see it. They talk about the standard model. Oh, this is the most perfect arranged, perfect thing. It does so much. It's magical. It cures everything and fixes everything. You know, and it doesn't do anything. It's convoluted mush. It doesn't explain anything. It doesn't work. It doesn't do anything. Yeah, well, I'm just, do I have to know that you're back? I mean, is that really, my neurons are going to be completely confused if you don't let me know you're here? But whatever, it's fine, whatever. I'm just saying I don't play that. Homie, don't play, hello, I'm here. No, it doesn't bother with that. So anyway, but yeah, I'm just saying it's all these subjects, every single look. And Benjamin Franklin made the honest mistake in the sense that, he didn't really have any huge clues for plus and minus, which way the electricity is moving. So he assigned the plus and minuses wrong, and it really is catastrophic to Maxwell's mathematics. Because now you have amperage going one way and voltage going the other way. It doesn't make any sense. Can't be happening. It doesn't work that way. The electrons are the pressure. The pressure can only move in one direction from high pressure to low pressure, so the amperage has to follow the voltage. But, they never fixed it. And then Maxwell's declaration that there's no magnetic monopoles for absolutely no good reason. I mean, whatever, it's like the number 6 equation and the number 5 equation basically says there's no magnetic monopoles. And you're just saying, says you. There's no reason to bother with that. And it's just so obvious that, the electrons and protons are doing exactly, the charge is exactly the same thing as magnets, the same inverse relationship between the north and south poles. It's doing exactly the same thing. How could you possibly think there could be some other mechanism besides charge creating dipoles and the dipoles being magnets? Duh. It's just that the magnetic field looks different than photons at a frequency. Photons at a frequency is different than blue here and then purple over here. That's a different pattern. It's all made out of the same stuff, but I'm just saying it's obviously a different pattern. And photons are just moving electrons, so we know it's just red force. The blue force. It's just electron sificuses that are making photons. And that just has to do with the fact that the electrons are on the outside of the half the electrons are on the outside of the atom. So I guess we could play the next video. Just having nerves. I don't like. Some reasons I just, my brain all of a sudden creates some sort of sense of paranoia and angst. And there's never any good reason for it. And I just said, what the hell is that? It's not like I had some catastrophically horrible thoughts, but they must be in there somehow. Somehow I said something or imagined something and my brain got triggered by it 4 hours ago. And it's still percolating, chemistry based on some perception of the threat or something to be uneasy about. Yep. It's just annoying. Brains are just such a pain in the ass. Alright, so we get rid of this first law thing and we have to load the second law video. Okay. That should be somewhere around here. No. Is it somewhere around here? There we go. Okay. So, how is this still here? I keep closing this and it's still there. Alright. So, second law. There it is. Okay. I have to burn through the commercial.
This is what Ivy League universities you can get into with...
So you don't have to endure this inane nonsense. And then we'll go through his silly intro and just skip all of that. Waste of time and blah blah blah. And just get to the fart part. Fart. Okay. And then we put the sound back on and pop out the window and pop the window on here. And there, we're ready to go.
We learned about Newton's first law of motion, which tells us that an object will continue its state of motion unless acted upon by some net force. The second law continues from there, describing what will happen if some net force is indeed present.
Okay, and right under the second law, Newton wrote this sentence, and I think this is verbatim. You apply twice the force, you will get twice the motion. 3 times the force, 3 times the motion. So he's making it clear by adding the 3 thing that there's no confusion here, that it's a complete proportionality. 3 units of force is 3 units of motion. 2 units of force is 2 units of motion. Basically saying the force is momentum. I mean, the motion is your momentum. You change your motion, your velocity, you're changing your momentum. Obviously, you double your velocity, you double your momentum. It's basically just saying there's a complete proportionality between, a complete equality even, between force and momentum. I mean, it can't be interpreted any other way. It's just so obvious. He's saying it's a direct equality. The force equals added momentum.
Whether from internal or external forces. This law tells us that force is equal to mass times acceleration.
So that's just such a gross lie. So he didn't even write what Newton wrote. Okay, and then this is just a lie. Newton didn't give a shit about acceleration. That wasn't a concept. The concept was merely the change in your velocity or the change in your net momentum, your quantity of motion. That's what he said. And they're just lying about the greatest scientist in history, because they can get away with it, because they all lie about him. But that's all this is. So he's teaching kids with an absolute lie. That's not what Newton said. Force equals mass, the change in your mass times your velocity. That's what he wrote. That's what he stated. The change in your momentum.
This is summarized in the following equation, F equals ma.
Yeah, what do you mean summarized? You just said the definition is exactly that. What's the summary? Where's the summary? That's not a summary. That's just you writing it in shorthand. But you're writing exactly what you said Newton said, which he didn't say. Oh, it's just such cheating. And again, the acceleration only exists because then they can do their dt over dt thingy and create this fake notion that seconds are times seconds, when all of the seconds in all of the units is 1 second. So you can know that every single s is supposed to have a 1 in front of it. And obviously it wouldn't make any sense to do 1 second times 1 second, would it? No, it wouldn't make any sense at all.
What it means is that we can do quantitative calculations relating the magnitude of a force applied to an object, the mass of the object, and the magnitude of the acceleration.
So again, the magnitude of the acceleration just has to do with them claiming that somehow per second means second squared. So they think because you could move 4 seconds that somehow I just square the seconds. It could be 6 seconds, it could be 7 seconds, doesn't matter. Somehow I square something. What am I squaring? And why would I square it when I can change how many seconds I'm applying the constant force. So it's just such a, like I said, it's just a gigantic distortion of reality. The number of seconds is variable. There's no squared function. You have to multiply the rate of your acceleration times the actual number of seconds you're accelerating. You can't just square the acceleration. And that's what they're doing, though.
That object will experience. And it shows the derivation of...
So there it is, right there. 1 meter per second squared. That second is just like the 1 meter, just like the 1 kilogram, just like the 1 Newton. It's 1, 1. It should be a 1 in front of that S. That S isn't any number of seconds. That S is a specific 1 second. It's 1 meter per 1 second. That's what that means. And they, you know, like I said, they're just cheating right there in front of you.
Of the Newton as the SI unit of force when we plug in 1 kilogram.
So we know a Newton is just a tenth of a joule, so why play all these games? We can convert it all into watts. We could all just use one fucking word, and they don't even have the integrity to say, yes, let's just use one fucking word for what a unit of energy is. And then we can all understand what that unit is, and then we can understand 0.4 of that unit, or 1/1,000,000th of that unit, or 10 times that unit. We could all understand it, but they just keep switching this crap and saying somehow the weight that something's applying is in newtons, but its momentum is somehow in some other fucking goddamn bullshit, in the sense of mv squared being in joules, when it's mv. It's a mass moving a velocity.
And 1 meter per second squared.
So there's no second squared. That's just a lie. Newton didn't write that. Newton didn't say that. Newton didn't imply that. Newton didn't go per second per second. Newton wasn't a foolish idiot.
Mass and acceleration. There are a number of things we can say about this equation, which is tiny but powerful.
It's silly and nonsensical, and it's really just force equals the change. You didn't even put the change part in there, okay, of your mass times your velocity. And obviously the force isn't going to change your mass, so we're just really saying the force will equal the change in your velocity.
First, it means that heavier objects will require the application of greater force in order to achieve the same acceleration.
Right, and so this is just saying that basically in gravity, your mass is the number of atoms, which could be equated to the amount of sail on your sailboat. So the bigger the mass, the bigger the wind catcher. You're going to catch gravity. How many atoms you have, how many electrons and protons you have will decide how much force, how many Sisyphuses you can collect. And the fewer atoms you have, the fewer electrons and protons, the fewer force bits, the fewer Sisyphuses you can collect, obviously. So yes, in the same unit of time, the tennis ball collects a tiny amount of force compared to the big heavy iron thing that has a ton of atoms to collect force with. So obviously when the anvil hits the barbell hits the ground, it's going to make a huge energy impact because it collected a lot more Sisyphuses. The tennis ball makes a minor impact because it didn't collect hardly any by comparison.
As lighter objects, with acceleration being equal to force divided by mass. If we want...
So again, the acceleration isn't the force divided by the mass. It's just not true, and it's just nonsense. Acceleration is just a useless concept. All you're doing is changing the velocity. You're adding Sisyphuses or subtracting. That's all you're doing. You're adding force or subtracting force. That's all you need to know.
Want these objects of varying masses each to accelerate at 1 meter per second squared. These are the magnitudes of the forces that must be applied in...
No, it's the same force that must end up collecting. So when they hit the ground, they'll also have this much higher impact on the ground itself because it's just collecting momentum. You're taking a mass, giving it velocity. You're creating momentum. That's what the force does. It creates momentum.
In order for the math to work out. This also means that the second law can be rephrased to state that the acceleration an object experiences will be directly proportional to the force applied.
So again, instead of saying acceleration, you should say the change in your mass times your velocity, the change in your momentum. That's what Newton said.
And inversely proportional to its mass. It is important to note that the net force is the sum of all the forces acting on an object.
All right, so this is where their force diagrams are just useless because these are all fictitious forces. These are places where you will lose your energy. They're contacts that will suck your energy away. They are not forces. They are not counter forces. They're just places where you can release your pressure.
If multiple forces are acting on an object, which is often the case, we will need to represent them all in a free body diagram and then add up all the vectors to find the net force.
Right. So, yes, I mean, you can do it this way. You can have this false notion that, at first they don't think gravity is a force, but then they draw the vector as if it's a force. But again, the friction and other things is not a force. It's a sink. It's a way you lose energy. It's not some countering force. It's where your force goes. You're losing it to some other object. The other object's now moving. It's hot. It's got moving pieces of matter because you gave away your movement.
Which will tell us the direction of the acceleration that will occur in response to the net force. This kind of vector addition allows us to make predictions about the motion of an object.
Right, and their predictions are absolutely wrong. So, like the rolling ball, they predict that it would go half its speed halfway down the track because they're not accounting for the fact that the friction, the arrow for friction, changes with velocity. So some basic fact like that they haven't even gotten right. They think the friction arrow is always the same, when no, it's completely different based on the velocity. Obviously. So it's a huge miss. I mean, for them not to realize that friction changes with velocity is just so stupid.
Even when it is being pushed or pulled in a variety of ways. Since forces are vectors, they can be split up into x and y components, which will be useful for doing calculations in certain scenarios that we will investigate later.
Yeah, but it doesn't really happen. The argument would be is the elemental matter is doing that calculation. And, the carriers, I would argue that electrons can carry 2 or 3 dimensional motion. That is, they can only move in this dimension, like one of these vectors. They can't move all of those vectors. They can just move one of them, and they can move one vector in this direction, and then they can move one vector in this direction. So they always have to obey the concept that these dimensions of motion are not shared, that they're independent.
Newton's second law of motion has an incredible range of applications, as it can be applied to any force that exists, and it describes the motion of all accelerating objects in the universe. We can even use it to do things like...
So that's a huge exaggeration, I would argue, right? What exactly it's just saying? It's just saying the force, a unit of force, equals a unit of mass times velocity, a unit of momentum. So it's just saying force equals momentum. Now that's useful in understanding that, the force is essentially equivalent to momentum, and what you could argue is the force is just something matter carries. So when matter's moving, it's carrying force because the force equals momentum. So it just perfectly fits with the idea that there's pushers in the universe and there's the things getting pushed. And so it fits perfectly with that model. But to say it's useful for something else, I don't really understand what the use would be, except to understand that force equals momentum. That force is just a form of momentum. Photons hitting you is a form of momentum.
Calculate the masses of faraway celestial objects. But for right now, we will just stick to the basics. So let's check comprehension.
Yeah, well, that was a nothing. So a big hype about all the wonderful things F equals ma does, and no real demonstration of what it really does. No proof that it does anything miraculous. And again, the only thing that's really important is understanding that force is just carried by matter. That's the really important takeaway, is to understand that if matter is moving, it has force, and it can give the force away. Alright, let's see. Ivy League sucks. That's just a useless statement, frankly. Where did the force come from originally? Well, that's like asking where did the matter come from originally? What's the point? You really think that there's somebody who someday will be able to answer that question? You really think there's going to be some way for somebody to find how to make matter, or to make force, or to make a universe? Not going to happen. The fact that it exists, you can make up all kinds of scenarios. I could just say it's error code in the universe. The universe makes a mistake, and a little bit goes flying off in the universe. I don't know. But it doesn't matter. There's a mechanical process, just like evolution. I could say, we evolved from a single atom. Technically we did. So, it's a huge distance and a huge gap, but the fact is that's what happened. So we know that the matter evolves also. So the universe evolved to make matter. But, do you think somebody's going to tell you how it made matter and how it made energy? I don't think somebody's ever going to answer that question. Ever. I know the answer isn't God done it. Because then you still have to explain who done God. It's just such an irritating question, just for that reason. It just implies that if somehow we don't know what Poof's universe is, that somehow now the door is open to mysticism and woo. When no, it isn't. Alright, force equals mv, exactly. Yes, it's that simple. Force is momentum. The little bits, the Sisyphuses, have a momentum, and they're essentially sharing it with the boulder. So it's just like you're just saying, look, the Sisyphus is flying, and he's now going to carry a boulder. It's the same idea. It can only carry it with the energy it has. So it has to share its motion, its mass and velocity. It shares it with the new mass, and now you have a much lower velocity because you have this much larger mass. Let's see. Why is Professor Dave like this? I don't know what you're saying. What's your point? Why is he a jerk and a dork and an asswipe and a fucktard? I guess because he had shitty parents? I don't know. He has kind of slimy, oily hair. Ew. I don't know. So there's lots of things you could pick on. Let's see. You seem to have been do not God your whole existence. Well, whatever. Yeah, I'm sorry. I didn't believe. They told me the God story, and they told me that story the same time they told me the Santa Claus story and the Easter Rabbit story, and I figured out pretty quick. Oh, this is just one of those silly stories you're telling me. Oh, okay. And the more you thought about it, the more ludicrous it became. I knew my penis was pretty important. And as soon as I found out that the book doesn't like my penis, religion became very uninteresting. Fuck God. If God doesn't like penis, then he can go to hell. That was just too ridiculous for me, oh yeah, I'm going to hang out with a god who thinks penises are evil. Fuck you. You're too silly. But anyway, the whole idea of, like I said, it doesn't take long for you to see all these little things that you think are very interesting. Like, I go out in my yard and I'm having conversations with bugs. I find an interesting bug and I play with it for a while with a stick or something. And, how you doing? What you doing there, bug? How you do that? Well, what's that little thing hanging off your butt? But you see how it all gets crushed and destroyed. It's just, I remember I had a pet lizard, and I used to hang out and sit in the sun we had one of those open garages, with just half brick walls on either side. And it would sit there, in the sun. And the fucking neighbor killed it because he thought it was a pest of some kind. And you're just like, what the fuck? So I went through the whole process of burying it and all that shit. And then I dug it up, a month or two later, and saw it all dehydrated and bony and shit. And I just said, yeah, no, there can't be a God. Why the fuck would God do this to my lizard? My lizard wasn't hurting anybody. If there was a God, he wouldn't have killed the fucking lizard. I mean, it was that kind of simple. If he was an all-knowing God, he would know it's going to hurt my feelings if my lizard gets killed. So don't kill my fucking lizard. But enough of that. That's almost more irrelevant to this physics subject than how ugly Dave is. Yeah. Alright, let's see. Let's find the third law. Let's see. Third law. There it is. Okay, hit that one.
With Plymouth Rock, I never want...
Okay. Yeah, fuck you. 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 Alright. Fuck you some more. He knows a lot about the science stuff. Professor Dave farts a lot. Okay. Shit. Alright, that should be working. Should be okay. Hit the button, Gary. We talked about the first law, then we talked about the second law, and I'll just do this extra talking for no reason, so the video is only really 2 minutes.
After learning about Newton's first law of motion regarding inertia, as well as the second law regarding the proportionality of force and acceleration, we are ready to round out the trio and look at Newton's third law of motion. This is most famously stated as follows. For every action, there is an equal and opposite reaction.
Right. Now, that's the wrong part, really. There's no... The action is, I have $10. I give $5 away to, say, a bowling pin. I'm the bowling ball. I gave $5 away. There's no opposite reaction that makes me have only $5. The action of giving it away is the only action you need. There's no opposite reaction. And the same thing for like a spaceship. If I push, like the fire extinguisher, you use the fire extinguisher to move in space. Well, that's the most obvious example in the sense that all you're doing is pointing a nozzle in a direction and you have a tank full of stuff that's going in all directions. And you keep giving away only one direction. So it means you still have stuff hitting the tank in all the other directions except the direction you gave away. So now you, of course, are going to go the opposite direction because you gave away all your stuff going this way. Well, a bunch of it. You gave a bunch of stuff going this way away. So now you still have all the stuff going that way. And so you don't have a balance anymore. Your tank is imbalanced by the hole you made in it. Even with a convoluted hose, the hole is still in the same place. That way. Okay. So that's a better understanding, in my opinion, of the third law. Is that all you're doing is you have a condition. And if I'm relative to you, we both have the same condition, and then you are going to change your condition by giving away force that you have in some direction. And once you give away force in that direction, the force you still have going the other way is now going to move you. You've changed your balance. So that's all you can do. The third law is just saying for every change in your balance and every change in an interaction with something else and you changed its balance, your balance must have also changed. And that's what appears to be an equal and opposite reaction, but there's really no opposite reaction. There's just the one action. So the Newton's cradle goes in and hits the other ball. There's no opposite reaction. The energy just clean and obviously almost, it's like so obvious. There's no acceleration, there's no deceleration. The ball comes in and the energy just goes right into the other ball. It's that smooth. One ball doesn't slow down and the other one speed up. It just moves the force from one right into the other. The $10 just smoothly goes out of my pocket and into his. No opposite reaction.
While this is often quoted out of context for metaphorical purposes, in physics it means something specific and quantitative. It means that if two objects interact, the forces they impart on each other will be equal in magnitude and opposite in direction.
So it's just really not true. But what they will do is share their condition. And if I get something from them, then they lost what they gave me. That's the simpler argument.
Think of a car hitting a brick wall. The car imparts an action force on the wall from its motion, and the wall imparts a reaction force right back on the car.
So that doesn't happen. There's no reaction force. There's obviously the force of the car. The wall won't accept the motion, so the car has to accept the change. All the change has to happen to the car because the wall is saying, I'm not going to change. Come on, not difficult.
Bringing it to a quick stop. These vectors are equal in length and point in opposite directions. What this also means is that there can never be a single isolated force, as any force is an interaction. Forces must always exist in pairs.
Wrong.
As you sit in your chair,
it's obviously isolated. There's obviously in a three-dimensional, and this is something Newton also argued and proved. So before he did the three laws, he explained the bucket experiment and the spinning stick experiment with balls on it, and how there's no way to perceive this as being a relative thing. Motion is something objects actually have. Some object actually has the motion. And so he already knew back then that he needed to make this argument against relativity because there was a bunch of people talking some fudgy crap that nothing's absolutely moving anywhere. And his argument was, well, it's clear that it is absolutely moving because spinning the universe isn't going to make the ball rise. And it's not going to make the water slide up the side of the bucket. It's not going to happen. It's not reversible. You can't just make up who has the energy. One object actually has it in real three-dimensional space terms. And we can usually see which one has it, as long as we understand, yes, the whole universe isn't spinning in the opposite direction. We're not being fooled, by some sense that, I throw a baseball and the whole universe moved in the opposite direction. That didn't happen.
right now, the force of gravity is pulling you down towards the center of the earth.
All right, so they all say this pull part. So why was that the word we use? Why is that the idea? So they never say you're getting pushed down. Why? Why don't they ever say it that way? How do they know how the bent geodesic is applying its force, right? It's because they're using this silly dent in a curtain thing, right? They put a curtain out and put an object in it and it makes a curve. And they're thinking, well, gravity is going to push it down. What? So gravity is going to push it down? But you're saying it's getting pulled down. How does gravity pulling it down. So it doesn't make any sense. From their own analogies, it doesn't even make any sense to keep using this pull word when it seems sort of obvious that the opposite of a light bulb would create a convergence force, a force that's going to pull you into the light bulb.
But something called the
pushing you.
normal force points straight up with the same magnitude, which is why you remain perfectly still.
All
We
right.
will learn more about this force.
So there's no point in saying you remain perfectly still because you can feel your ass impacting the ground all the time. If I was perfectly still, I shouldn't be feeling anything. So it's the very fact that I'm not perfectly still, that the force is constantly pushing parts of me into the earth, and the earth is pushing back. And I'm feeling the earth push me back. I can't feel the gravity because the gravity moves every piece of me exactly the same. So I can't feel any difference. But the fact is, when the earth pushes back up, I can feel that because the earth only pushes on my ass. It only pushes on the surface. It doesn't push every one of my atoms. It just pushes my ass. So I feel the earth pushing me up. I don't feel gravity pushing me down. But it's silly to say I'm not moving. Obviously my matter is oscillating in the gravity between the force of gravity pushing me in, creating higher pressure, and then the earth, having absorbed the higher pressure, pushing me back up.
Later. The third law can sometimes be confusing because it would seem to imply that no object could ever move, since any force accelerating an object must be paired with another in the opposite direction.
All right, so it really isn't got to be paired with any force in an opposite direction. Again, you're just giving away syphicuses. There's no opposite, I gave you back syphicuses in the opposite direction. I already had syphicuses in the opposite direction. You didn't have to give me any. So there's only an exchange of actual force arrows, actual arrows, and they can't be destroyed. So you know the force arrows have to move that object, or they have to go somewhere. They can't go nowhere.
For this reason, we must understand that when assessing the motion of an object, we consider only the forces acting upon that object, and not the forces that it applies on other objects.
So that doesn't, how do you even make any sense out of that? Only the forces acting on an object contribute to the motion of that object. It just doesn't, they're both interacting, they're both imposing their condition on each other. And the idea is them to have some, happy compromise, and both end up, basically, I give you $5 and then you give me $5 back, something like that.
When hammering a nail into a piece of wood, the hammer imparts force onto the nail, and the nail imparts force.
All right, so it's just wrong to say that the nail imparts any force. So it is just the hammer sharing its momentum, and it can't give it all away, so the hammer will often bounce off the nail because there's not enough time and the way the conversion has to happen. Basically, you have to convert the currency. The nail can only accept nickels, and you have a bunch of quarters. So you have to convert the quarters into nickels to give it to the nail because it's smaller and has fewer atoms and all that kind of argument. So to give your velocity to something that's not the same mass as you, it gets complicated. But if the nail was the same mass as the hammer, well, then the energy will go in much easier because it'll just transfer
Onto the hammer. But the nail is driven into the wood because there is a net force.
So it's just really complicated to do this example because this isn't like hitting a nail in space. If you hit the nail in space, obviously the amount of energy to get into the nail will be huge. But obviously because the nail is penetrating the wood and there's all kinds of friction, you're using up a ton of the energy to heat the wood and heat the nail. So it's hard to see that you've actually imparted a tremendous amount of energy because the nail doesn't look like it goes very far. But it used a lot of force.
Acting upon the nail from the motion of the hammer. Likewise, the hammer has two forces operating upon it, the downward force from your arm and the upward force from the nail. That's why when you strike the nail, the hammer stops moving at roughly the location where the impact occurs.
Right, but that's, again, it depends on what nail you're hitting. You often get a bounce from a hammer. So, but there's no counter force. It's just wrong to say there's a counter force. There's either an acceptance of the motion or the motion is rejected because there's too much friction.
So if we are looking at the nail, we only consider the forces acting on the nail. If looking at the hammer, we only consider the forces acting on the hammer. These are different systems.
I don't know why that is a thing, so I never even heard it described that way. We're talking about a transfer, it's a collision, and you're just saying, can the object I hit move or can't it? So if I hit another car, well then I can impart my motion into the car. But if I hit the brick wall, then all the motion has to be in my pieces. All my pieces have to bend and break because there's no other pieces that are available to absorb the energy.
And this is...
I mean, it's kind of obvious that if you crash two cars into each other, you crush a lot more fenders than if I crash, in the two cars. But it'll be the same amount of crushing as if I crash a car at 100 miles an hour into a brick wall. I'll get the same amount of car crush as if I have two 50-mile-an-hour cars crash into each other. So there's the same amount of crushing because I now have two things that are getting crushed, so they'll look like less energy, but it's the same amount of crushing. You just have to follow the energies in clumps, and you just follow the clumps. You just say, where are the clumps going?
The context in which the third law is best understood. Let's look at another example. When a rock falls to the ground, the gravitational force from the Earth causes the object to accelerate towards the Earth. But it is also the case that the Earth is accelerating towards the rock.
All right, so it's just ridiculous because obviously the proportion of gravity the rock can create is so minuscule that it would be an incalculable amount. And it's implying that the Earth's force is somehow equal to the rock's force. It's just not true. So this part of the Earth is not going to be affected because the Earth has a giant dampening effect. It's like Tesla saying I'm going to shoot voltage into the ground and then I'm going to receive the voltage in France. Well, you can't do that because the Earth dampens anything you stick into it. All vibrations are lost to the giant absorption of the dilution. It's so diluted that it's like dropping food coloring in the Atlantic Ocean. It's not going to turn it a color.
This must be true according to the third law.
Nonsense.
Of course, we don't notice this in everyday experience because the acceleration of each object is inversely proportional to its mass. The rock is very light, so the rock accelerates quickly. The Earth is very heavy, so Earth's acceleration is completely...
So this really doesn't have anything to do with the equal and opposite reaction that you're supposed to be talking about at contact. We're not talking about what causes the rock to move in gravity. That's not the third law. The third law is about what happens when there's an impact, when there's a collision. The third law has nothing to do with the mechanisms that cause things to move.
Negligible. This may seem a bit...
the forces that cause things to move.
Bit abstract, but it is important to be able to rationalize forces in this way. So there you have it, the law of...
Rationalize is the key word there. So again, it's just the whole thing is just lost in the sense that they're talking around the subject and not getting to the point that the force is something carried by matter. And it's that simple. And the force is the part that gives it momentum, because the force is the part that gives it velocity. There's no velocity without the force. The force is the quantity that creates velocity. Maybe that's the simplest statement I could make. Alright, so let's see what we got here. It makes total sense. How would you explain suction as a push? Well, you can't understand that if I evacuate the energy or the matter that's moving from a container, okay, that the pushing force on the outside is going to be much greater than the pushing force inside. It's almost like saying that, you know, if I have an inside that doesn't have any mass that can hold force, wouldn't all the force going out of the container be almost non-existent? It has to come from the outside to get inside the container, doesn't it? The force has to go through the container and get to the inside. So in a way, you can understand that without matter, there's no way to transfer force to the matter of the object. So obviously the force is going to be the air pressure pushing it in. Obviously in space I can't create that scenario because there's no air pressure, right? We're talking about matter pushing something, and there's no matter. So if the Earth was made of force, then I wouldn't have a problem falling into the force. Let's see how else to say that. But I mean, it's just obvious that the suction is a matter that only can be created in an atmosphere that's pressurized, a field that's pressurized. But you could argue that every piece of matter in space is essentially a vessel that's pressurized. There's more pressure on the outside pushing in. I mean, that's why everything sticks together. I mean, you're just, in a sense, if you're sucking the air out of something, you're sucking the matter that's creating pressure. So you're sucking the internal pressure out, so the external pressure gets stronger. I don't know how else to make it any simpler than that. The only thing that creates the air pressure is the molecules in the air that are getting pushed into each other by gravity. So gravity is pushing on the air, all the air molecules. They can't go into the ground, so they bounce off of each other and get stuck in this layer. The layer's pressurized. If I pull the atoms out of something, then the atoms on the outside are going to keep pushing, and there's nothing on the inside to push back. I mean, all pulls are just the absence of a push. I'm just saying that's, if I was going to have Gary's laws, that would be one of the laws. You know, that it's a push-averse. There's just no elemental pull. There's no way for anything to elementally pull, because that requires it to have grasping appendages or something. And you know, and then it still has to push on the object to get it to move. It can't literally just pull on it. I mean, it's just obvious there's only one way to interact in the universe, and that's to have a collision. That is to have proximity. You have to be close enough to impact it. Obviously, everything, electrons don't really collide. They bang into each other's force, so to speak. So the Sisyphuses mediate the actual collision. Boulders can't hit boulders. You know, there's always going to end up being a Sisyphus in the way that's going to prevent the boulders from hitting each other. And such. And so forth and whatnot. All right. So I'll give you a little more time, and just figure I'm getting a little tired. So if you don't have anything to contribute, call it an evening and such. Let's see what the room statistics are. 12. Well, it's not terrible. Well, it is terrible, but relative to awful, it's not as bad, right? Awful's worse than terrible, right? yeah, something like that. And such. Wow, it had a big dip a half hour ago. Big dip. Yeah, it's just kind of funny. It went from like 12 to 2. That's funny. It had a high of 16. So, yeah, but we're just kind of slopping along. Blah, blah, blah. And such. So, back to the chat. See if there's anything. Alright, 2-minute warning or something like that. So if there's something you'd like me to clarify, bring it up now, or too late otherwise. Fat. Well, that's not very useful. So yeah, being fat, I just don't get it in some ways. I mean, I know it's such a problem. I mean, look, I smoke. I'm addicted to nicotine, so I understand how hard it is to. But it's not like you have to starve to death. It's really not. All you have to do is figure out that you got to eat certain foods to keep your metabolism moving, so you don't digest everything you eat. That you don't absorb all the calories. That's a trick you can use. Or you can just reduce the number of calories. But the trick is you get rid of the weight. You go through a little bit of inconvenience. Once it's gone, you can theoretically eat almost the same amount of food that you were eating before, because you weren't getting fatter. So let's say you gain 50 pounds and you stay 50 pounds overweight. Theoretically, all you have to do is get rid of the 50 pounds and eat a tiny bit less than that. Just because you end up metabolizing more food, just because you're fat, you use more energy. But you really will be able to eat pretty much what you were eating before, because you were maintaining your weight. And you just have to trick your metabolism. Your metabolism wants you to be fat. And you just have to understand that that's just an evolution thing. And that I don't have to be fat. But it's really just about, the logic is just make the stuff go through you a little quicker, and then you'll be able to eat more and gain less. But that can be sort of uncomfortable, I would imagine. But the other alternative is just cut out a meal. I only eat once a day. Well, in the summer, I have a couple of tomatoes in the middle of the day just because I grow them, and so I eat them. So I do have a snack in the middle of the day. But generally speaking, I just have one meal. And it's good enough for me. It works. But anyway, not really the physics I want to talk about anyway. How do you feel about all these Wikipedia power mods? Well, I already pointed out how I feel about them. I drew them as being living in an outhouse. They're poo, purveyors of poo. Just shit-talking douches. It's just too bad that just shows how little integrity there is in academia and the people who are called authorities. They're not experts. So they have badges, but they don't really have knowledge. They just have their badge. Let's see. I saw you talked about it on the first short. Yes. I don't like shorts, so I don't make them. But it's just so. I don't. The subjects all deserve kind of a deep conversation, not a superficial, trivial conversation. And even saying Wikipedia sucks, it should be explained why it sucks. How it could maybe fix some of its suck. but it's really hard to fix communities, so as soon as you make one of these groups, it's really hard to steer it and to have it be principled. And so it's almost like just even government in general. You're better off with a benevolent dictator, than you are with a common denominator democratically elected moron. And that's just a sad truth. So what Wikipedia needs is a good dictator, somebody who really cares about getting to the truth, and they don't have that. I mean, I actually knew the guy who created Wikipedia. We had way back in the before Google days, we were talking about discussing internet indexing and how the internet worked, and Yahoo and Alta Vista and all these companies that were starting to generate search engines, and what was the danger, and how were people controlling the results, and were they paid results, or were there advertisements in the results, and how was it getting distorted and perverted. And he was basically arguing that in a sense he could use his Wikipedia model as a way of indexing the entire internet. And I sort of said, no, it ain't going to work, because it's community-based, and human beings are all going to be corrupt, and every subject's going to get owned by some jackass who has a bunch of personal interests. So you really can't, you have to get people out of it as much as possible, and have them objectively look at stuff, that is, have no personal interest in their choices. So they really can't ever decide to place their own property in a ranking. They can only rank the other stuff, that kind of thing. You have to try to take people's biases out, and it's really hard to do. And so obviously the algorithm idea is, yes, that's a way of doing it, but the algorithm is just measuring popularity instead of measuring relevance. So the algorithm was so easy to cheat. So then they invented this whole thing called SEO, where search engine optimization, they called it, and it was just a way of gaming the search engines and forcing spamming. It's just spam, 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 spam. That's all it was about. And that was a total disaster, ruined search engines, because they never took it serious that they have to have metadata on the web pages, and that if people lie on their web page, then those people should lose their access on the internet, that kind of thing. You have to punish people for bad behavior. You can't reward them for it. And there was no mechanism to punish the bad behaviors. So that was the failure, and I predicted the failure of search engines 20 years ago. All right. Let's see. I edit on Wikipedia and have around 1,500 edits, but it's hilarious how they love to manipulate the truth. Yeah, well, I'm just saying, it's obviously the editors are, you have to say what they want to hear, and that's all that's possible. So there's nothing, they're just an authority. There's just no way of getting around the fact that they're just declared authorities, and their policing is not honest and doesn't have any integrity. They're clearly have agenda, personal agenda, and they're allowing their personal agenda to influence their objectivity. People are just really bad judges, it's just, it's, yeah. They're so easily biased. Commenters have been much better today. Well, I don't know if they've, yes, it's better. I mean, all the, rubbish poo comments aren't here, but I don't know if it's been terribly relevant either. Well, you can't really ban these professional trolls because they have so many sock accounts. So, it's almost a joke to say you blocked or banned one of them, because they just keep coming back. It's just sad that there's so many people that just want to disrupt and break, and they just don't have any capacity to make a positive contribution. All they can do is throw rocks. Well, from my perspective, you can't get a YouTube account without having a mobile phone now, so you can only have so many mobile phone numbers, I guess. But there must be people who have a bunch of them. I mean, there's so many VPN tricks. There's so many things out there that just allow people to do all this, hide your identity. And they pretend that all these services are to protect people. This is how you protect yourself. These are all the tools of the spammers. It's just, so it's almost like, 15 years ago on the internet, everybody was selling spam software, and all the spam software was all spam. It was all injecting your computer full of viruses so it could make you feel like your computer needed virus software. I mean, it was just so ironic. I mean, they were, putting viruses on your computer and then claiming, look, I cleaned your computer of the viruses I put on it. It's so bad. So, need a physics comment. Or else. What was the internet like during 9/11? Was wondering about that today. Well, 9/11 was really a long time ago. So I still had a TV when 9/11 happened. So shortly after that I got rid of it. But I remember watching it all on TV. I just happened to be watching the news when it happened. And so, it was all just happening live right there on TV. Pretty weird. And so I can't even, we're probably still using a 286 computer, still dial-up modem. I was probably still on one of those services that, put the ads on the top and bottom of the web page. And but it was free, so I was always using whatever I could get is free. AOL was kind of funny because you could sign up and then get your free month, and then you just waited 2 months and you get another free month, and then you just wait 2 months and get another free month. So it was kind of a it was fun. I don't think I ever paid AOL. I don't think I paid anybody. It just wasn't something I was willing to do. But I was on the internet early on, and there was so much you could get. You could get all kinds of resource stuff. I mean, I learned assembly programming, because I can't remember his name, but he became kind of famous selling crappy spyware software and shit. He became one of the spammers actually. But he gave away so much stuff in the early days, and so just a huge reservoir of, information that would have been so hard to get. Because books are always dated. Any programming or computer book back then, it was always 5 years old or 6 years old, and so it was already useless. But anyway, it was just very... the internet was fun in the early days, and now it's just tedious. Alright, physics question. How would you summarize your physics theory in a few sentences for simple Joes? Well, again, it's just no point. I summarized it pretty simple. I said 2 plus 2 plus 3. There's two kinds of force, two kinds of matter, three kinds of interactions, and that's all that you need to know, frankly. That's the only real mechanical part of the system. Everything else is just a byproduct of those rules. Those three rules, pushing, reflecting, and converting, create everything. So, you don't need anything else. Because that creates charge. That creates electrons and protons. And once you have electrons and protons, game on. You have atoms, and then you have molecules, and then you have all this shit. And the fact that the matter absorbs the force, in the sense of it truly absorbs force, in the sense that it prevents force from getting where it was going. And that simple fact makes gravity really understandable. That the force hitting me from the open, free universe hits me now. The force that should have hit me from below through the earth hasn't gotten to me yet. And I'm stuck in that differential. There's 50 Kelvin of heat coming down from the universe, and there's only 49 at this exact moment coming up from the earth. And so I'm missing 1 Kelvin, and that's what I'm falling into, is that differential. But I mean, the subjects are kind of diverse. You have to admit that they are, you have energy, gravity, then you have the whole quantum mechanics crap that's based on the two slits. So how do I summarize and say, well, all of this stuff made out of wave particle, so all the wave part is wrong. It's about frequencies. It's about a period between events. It's not about anything waving. It's baseballs hitting a stick. It's not waves hitting anything. It is a particle physics. The universe is particle physics. The physics is about particles being pushed by force. And there's waves are just irrelevant. In what ways does adjusting the angle of the launch help optimize the horizontal velocity of a projectile? Help the horizontal velocity. Well, that's just the vector math. I mean, it's components, and you're just going to end up doing the hypotenuse. Now, the tricky part is elementally, I can't. The hypotenuse isn't twice as long as this plus this, right? So if I add this, a 1 this way and a 1 this way, I don't get a 2 this way. But that's just because of what three-dimensional space does to motion in two directions. So motion in two directions turns into that hypotenuse. It doesn't turn into a line twice as long. So, so even though it should be a line twice as long, it isn't. But, it's just the square rule, right? I make a square, the diagonal isn't twice as long as the sides, two sides, But, I mean, the forces are theoretically independent, so any force hitting you this way, when you already have motion this way, will combine and create a new motion. But the new velocity won't be twice. So if this is one velocity and this is one velocity, when the two are combined, you're only going to get 1.4 velocity, or whatever the number is. You claim that physicists square acceleration. I don't claim it. It's just an absolute fact that when they go through their derivative, they end up putting seconds in the equation twice and then multiplying the seconds times the seconds. It's just a fact that they say the units are now squared. That 1 second times 1 second equals second squared. 1 second times 1 second equals 1 second. So that's an absolute truth. Yet you can't show where this is done. Of course, I have shown it, so that's just a lie. This just shows that you are too stupid to do physics, so fuck you. I mean, you have the right name, tool. You're a tool. You're a dupe. You're an idiot. There's no derivative. I'm just saying, look, the argument is there's no such thing as this acceleration, so I don't have to create some formula that says what's the acceleration over an infinite number of seconds. There is no such concept. There's no such thing as a constant force in any sense whatsoever. So a force is applied over a specific number of seconds. You have to multiply the force times a specific amount of time the force was applied. You can't get a net value if you don't have a net amount of time. Saying per second is stupid and ludicrous. That's an absolute fact. You're driving down the road 60 miles an hour. It would be idiotic to say, I'm going 60 miles per hour per hour. So you're just going to get blocked, I think, because this is a waste of time. Okay, you can't make a video, you can't draw a picture. So until you can do one of those things and explain how dropping 4 units of distance in gravity means you collected 4 units of force. Well, why don't you explain how something that happens 9.8 meters per 1 second, why don't you explain how in 2 seconds it made 4 units of force? That's what you need to explain, asshole. I'm not really interested in these poorly written equations. 1 times seconds. What does that even mean? It's 1 second. 1. How about 1 times 2 times 1 times 2? What the fuck does that even mean? Yeah, it's obviously going to be 4 if it's 2 times 2. This is just pointless. Squaring units is completely a distortion of the reality. They never do it in any other circumstance. So you show me some other equation where when you multiply meters times meters, you end up with meters squared when it's 1 meter. Yeah, I'm saying 1 second times 1 second is 1 second. That obviously, it can't be anything other than 1 second. I mean, do you think 1 meter times 1 meter is 2 meters? Or meters squared? I mean, it's just a simple enough question. So again, this is just, okay, you know, there's no point. I'm not going to do this, right? There's no, what did I say? 2 times 2 equals 2. I didn't say that, shithead. So just fuck this nonsense. You're not going to answer my specific points. You're not going to show me any evidence that it takes 25 times the fuel to go 5 times as fast. Until you show me that, you have nothing. 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 I mean, it really is about experiments and evidence. That's the only reason you have the conversation. The only way you do detective work is you have to have a magnifying glass and you have to see the fingerprints and collect this and find that. It's the only way you can do this job. And so you need to test things. You need a laboratory. You need to do all that kind of crap. Where have you done any of that crap defending your silly notion that something moving twice the time in gravity has 4 times the energy? Where does that happen? Two units of gravity is not 4 units of energy. It's just obviously not. I mean, go ahead. I just don't see, this isn't that challenging, right? I mean, I'm sitting here and I say, look, okay, here's an analogy. I have 3 arms. I have 3 baseballs. I'm in space. And I just throw the baseballs. I throw 1 baseball, I get 1 velocity. I throw 2 baseballs, I just double whatever that velocity was. I throw the 3 baseballs all at once, I triple that velocity. Now, clearly, I didn't do 9 times the work. So how can the kinetic energy theorem survive that basic experiment that basically says there's no evidence of it? You certainly can't prove that going 3 times the velocity does 9 times the work, but you can't prove that I had to use 9 times the energy to make 3 times the velocity. There's no evidence of it. So deal with that analogy and explain where I just said something wrong, where I didn't accurately describe what actually happens. That somehow throwing 2 units of energy doesn't get me 2 units of velocity, when I'm sure every real physicist will concede, yes it will, because that's Newton's third law. Oh, I forgot to put it on live chat. Maybe there's a whole bunch of chat I didn't see. Who knows? Alright, I don't see anything. Okay. Oh, it's just so annoying that you have to play these silly games to do YouTube. I have to hit newest first or you don't see the comments. You have to hit live chat or you don't see the chat. I mean, it's just such bullshit. Why do university physics students not realize this? I don't know. That one is just so hard for me to understand, how all these other people heard the same shit I heard in high school and somehow they didn't react to it and say, oh, that sounds like shit. They made that up. You know. That's a little bit too wacky. You're going to have to show me, I mean, that's a UFO theory. You're going to have to show me extraordinary evidence if you're going to make an extraordinary claim. And they weren't even showing ordinary evidence. And it's just funny how everybody else falls for it and gets duped by it. But you're saying, why do people fall for religion? I mean, like I said, it was a non-starter right from the start. The whole thing was idiotic. They had me doing the Lord's Prayer at night, and I'm sitting there saying, and please God, don't kill Grammy, and don't kill my grandfather, and don't hurt my sisters, and please, please don't kill my parents. I'm having to plead with God not to kill everybody around me? I mean, it's like, why do I want to have anything to do with this loony God? I have to plead with him, not to harm us? It was like, your brain didn't say what the fuck when you're doing that? Why the fuck would I want a personal relationship with this fucking sadistic loony God who obliges me to beg him not to torture me? Please don't give me cancer. I mean, what the fuck? So yeah, I don't know. If people can fall for religion, then I guess they can fall for bullshit science. We have 156 billion neurons, yet we still believe in ghosts. Yes, it's just so pitiful. Obviously, it's not we. It's just them. But that's the whole point, is people don't know how to use their brains. I mean, that's, I made that video tonight. They just don't know what kind of resource it is, and they just squander all of that capacity. All of our brilliant reasoning skills, they just throw it all out the window, and polish their badges. Pitiful. The only way God can be real is if it were all one mind. Well, whatever that even, I don't buy into whatever that crap is. Mr. Natural, what a fantastic thing to see. Yes, I was been wondering about you. I was playing with my crystals the other day, and then I have the magnetic crap, and oh yeah, right here. You know, these are just such fantastic little magnets. I just I love them to pieces, but I don't know how to use them yet. But I'm saying I got to figure out an experiment because these are just so brilliant. You know, these they're little round magnets. You can put this thing into a block. You can do all kinds of things with it. You know, and they just, you know, they're each little magnets, and they go in a string, and they're, you know, you can pull, like I can start pulling them off, and they'll pull off in a string. I mean, it's just, you know, it's really quite, but anyway, so yeah, thank you. I really, I mean, I have, you know, my time is just so limited that I haven't gotten to everything you sent me. And some of the stuff, I'm just like, oh, I got to do something. And it's just so much that I'm trying to do, so I just never get to anything. But I have played with it, and I have enjoyed it. So it was, you know, it really was really nice of you. Thank you. It's a gift that keeps on giving. So, you know, and I wish I had told you that sooner. But anyway, it's just really great seeing you, and you know, that you're still kicking, so to speak. Still, you know, still fighting off the, you know, reality. Yeah, that's all we can do, right? Is try to reject reality, build an umbrella. If you say that 1 second times 1 second is 1 sec, I'm just saying 1 times 1 is 1, okay? You want to play some game, then we're just not I'm not going to play it, moron. Alright, the equation should be true no matter what it is. Just replace s with the number larger than 1. Why would I do that? The whole point of the relationship, it's 9.8 meters per 1 second. It's not 9.8 meters per any number of seconds. If I change the 1, I have to change the 9.8. So it's okay with me if you want to change the 9.8 to another number. But then if you do the equation that way, all right, it's still, the unit is still 1 second units. So you can't say it's 1.4 seconds per second. It's still 1 second that you're multiplying it by. So you can't fix that part. The unit is still 1 second. The meter is 1 meter. Anytime you have a unit, the unit stands for one of those units. There's always a 1 in front of the unit. All right, anyway, I'm not going to argue that forever. Just replace the S with a number. Okay, wait, I'm just not going to play the game. You want to play it somewhere else. That's just math jargon. It's semantics. It's game playing. It's smoke and mirrors. It's bullshit. Just doesn't have anything to do with the reality of the ratio. The ratio was built out of the concept of 1 unit of time, or 1 unit of mass, or 1 unit of something. Alright, solipsism is the only real logical conclusion for God. Well, again, you keep saying these kind of things, and that's your business, but I don't see anything. I don't see that. That just sounds like jargon to me. So you want to type jargon, it's okay, but it's just jargon from my perspective. That's a cool magnet. Yes, it is. Holy shit, you are retarded. Well, that's useless mush. So you obviously have a micro penis, and you're no doubt smell like anus. Slowing down with age, but still trucking. Yep, that's all we can do. The main argument for God as, well, you just keep doing it. I don't want to talk about this, so fuck you. I'm saying it's a completely illogical, nonsensical theory. That's all that has to be stated. It isn't a reasonable theory of reality. A psychotic, lunatic God who existed forever and then one day decided to make people. So he existed forever, and then it occurred to him, with his infinite intelligence that was all-knowing, but it took him an infinite amount of time to figure out, I'm going to make humans. Fuck you. I'm not interested, Gilbert. Just shove this crap. Okay, anyway. Let's see, math is just smoking mirrors. That is hilarious. Did I say that? No. MV equals MV. Well, that's pretty good math. I'm saying your formulas are crap. Your Schrodinger equation? Forky thing. Well, Forky thing stands for all the knowledge in the universe of what every single particle is doing. That's bullshit math. Alright, this isn't the way I argue, but it's still a pretty cool argument. Well, whatever, says you. Ugh. Yuck. Has no appeal to me. Certainly wouldn't convince me of anything. Jargon doesn't convince me of anything. And that's just jargon. It's like reading Schopenhauer or reading some of these philosophy books, and all they're full of is fucking jargon. Dropped my pencil. Alright. So, and again, to the math guy, like I said, why do you just keep evading the simple obligation I presented you? Show me a link to anything proving it's 25 times the fuel to go 5 times as fast, or give me an explanation how what I proved by just pointing out that in space all I have to do is throw 3 objects with 3 units of energy and I will get 3 times my velocity. So how is kinetic energy verified in absolute space where there's no variables getting in the way? Yeah, well, it's important because it's just another way of demonstrating how humans are so unreliable. So they've been very unreliable in their ethics conversations because they can't get the obvious that we're playing for suffering. That's the money we're putting on the table is suffering. We're gambling with it. So they can't get that philosophical notion. And then in this physics argument, it's the same kind of thing. So you're really just always combating religion and dogma and statements about religion, or life that are just bullshit. Life's a journey, not a destination. Silly sappyisms, that just don't make any sense at all. I mean, the destination is how many times did you get ruined? How paralyzed are you? How many diseases did you get? How horrible was your death? That's going to be part of the journey, and it's going to be part of the statement of what your life is. So that's the destination, is your ruin. That's your destination, ruin. Disease, disability, and death. But anyway, so it's just, yes, the physics is just another way for me to argue against the bias and prejudice that people have applied to their reasoning skills, because they're trying to force the facts to match their bullshit rather than the other way around, where you let the facts point to the truth. They're trying to force the facts to defend fables. I mean, it's a very natural thing, speaking of Mr. Natural, for me to go from making this kind of trying to think of the right word. It's not a crude philosophy argument, but it's just so bare and raw. And yes, and then you're just saying, well, what's the raw truth about the physics? Well, the physics is just as unyielding and brutally simple as the value equation. Human beings are basically saying, my little adventure, my little fable of my little special life is worth torturing animals for. I'm worth torture. And the simple argument is, not even close. You're not worth, you're not worth the horrible death of a mouse, And then the physics thing is basically wiping out any notion of any magic about our existence. We're just robots regurgitating our life experience. We banged into a few things and, it dented us, and now we beep, in a different way because of the dents. Let's see. Yes, you knew what the fuck was great as always, all the time. Look forward to them. I couldn't name anything better on the whole damn internet. Yeah, well, that's very nice and whatever, but that's kind of off the subject. All right, when you throw three, so here's his great explanation. So he can't draw anything, but this is this is the best we're going to get. When you throw three balls, your own mass yields more. So why are you saying that? How do you know any of this, whatever this yielding thing is? So you need more energy. Well, where did you demonstrate that? So if I use three springs instead of anything else, there's three springs. I launched the three springs. You're saying the three springs are creating 9 times the energy. I mean, it's an absolutely ludicrous argument to make. It's not happening. It didn't happen. The gun is doing the same thing. The gun has one explosion. How does the bullet get 2,000 joules and the gun only gets 2? How is that possible? All right, anyway, you need more energy to throw them as fast. That's just a lie. So you just made that up, okay? There's no evidence it took any more energy. So you're not going to link me any proof of that fact, that it would take more fuel if it were using gasoline or something else to ignite an explosion to launch the balls. There's no way you're going to demonstrate it would take 9 times the fuel to launch 3 of them versus launching 1 of them. It's just idiotic. It's the same exact event. It takes the same amount of fuel. Also note that the masses of the balls are very small. So that's the whole point, is to make the experiment demonstrate the big difference, like the bullet and the gun. You want to have as extreme a difference as possible so you can demonstrate how you're saying it's a preposterous amount of kinetic energy when no, it isn't. And all it is momentum, because it proves it, because my motion is only going to be the momentum. I'm not going to have any equal and opposite reaction to the kinetic energy. It's not going to play any role whatsoever. It's a decisive argument. It just dooms the whole thing. And here you are sitting here trying to rationalize bad theory. It's really bad theory, invented by a religious kook, defended by nonsense experiments, and here you are defending it for some reason. I mean, you're the puzzle. You're the thing that's confusing. Why the fuck do people do this? All right, it doesn't follow Newton's laws at all. Newton's laws are all about momentum, the third law especially. There's no example where the third law conserves kinetic energy. So you're just such a liar, so you're done. You get out of here with these lies. Fuck off. I mean, the gun and the bullet proves, okay, there's no third law followed. 2,000 joules goes one way, 2 joules goes the other way. How is that obeying the third law? It's just idiotic. Obviously, Newton didn't believe in kinetic energy. He wouldn't have written the third law if he thought the bullet actually has 2,000 joules and the gun only has 2 joules. If he actually believed that, why would he write the fucking third law? Ugh. So that's how desperate they are, though. So you give them you can't get a simpler experiment, right? I mean, you can't get much simpler, right? You're just saying, okay, I got a spring, I'm in space, okay, oops, I'm shorted. Yeah, causing an electric disturbance. All right, and all I'm going to do, I have the choice. I can launch 1 ball, I can launch 2 balls, or I can launch all 3. The same spring compression. If I launch 1, I get 1 unit of velocity. I launch 2, I get 2 units of velocity. Launch 3, I get 3 units of velocity. And he's claiming that this is 9 times the work. He's just going to argue that somehow it's 9 times the energy. When obviously it's only 3 units of energy. I only had to push the spring 3 times to compress it. I only put 3 units of energy in. And yet he's going to try to rationalize that somehow this is actually 9 units of energy in. Even though I did the work, it's only 3 units of energy. I mean, it's just crazy. It's so pathetically desperate. And why? Again, why? To defend a religious kook who talked about solitons and monads, who just had the wackiest, craziest bullshit theory of reality you could imagine. A guy famous for saying it is the best of all possible worlds because God wouldn't have it any other way. And this is right in the middle of, 1/4 of England's population dying from the plague. He's saying that while, giant, huge chunks of the population is being killed by diseases. And, people's wives are dying having kids. All this bullshit happened, all this horror. And he's spouting some crap about how it's the best of all possible worlds. And you have to wonder, that's a science lover? A science lover is defending that kind of crap? A science defender? I mean, it's just disgusting. I mean, it's like Jerry Falwell science, you're saying. So Jerry Falwell ends up doing a physics theory, and these assholes would defend it. Oh yeah, Jerry Falwell is a great physicist. Yeah. He really understood physics. That whole university he created did all kinds of great physics. Oh, fuck. I mean, it's just so goddamn ridiculous. Okay. Well, it's probably now past my bedtime, so I guess I probably should go. And such. So we did get an extra hour out of me, so you did well, commenters. Just showed up just in time to keep me clinging, and whatnot. So, and I get to make a couple of arguments over and over again, so that's always good too. So, emphasize them and such. All right. So till the next time. So yeah, in the most part, you were all quite well behaved. But you, yes, do tend to forget it's physics. I will do a live room on the Amendum channel, so then you'll have your chance to do that kind of crap. But I don't see any point because that's so much. It's so much harder to prove, that you're not worth torture. Yeah, I mean, it's a little. I can just give all the kinds of examples of how I know I'm not worth torture, so I'm sure you're not worth torture. If I'm not worth it, you can't be worth it, of course. It's just so obvious. Yes, it was just so damn charming to see you again, Mr. Natural. And so, yes, maybe you can pop in again sometime. I wish I had a schedule, but it's usually at night. Well, it's usually whatever this is, sometime between now and 2 hours ago. Yeah, something like that. So far, it's been a little bit regular, but it probably won't be every night. I mean, sooner or later, I'll get fatigued. Yeah, I just had Lyme disease again. It's just so funny, I moved to a place that's really urban, and yet I get Lyme disease again. For the 12th time. And just annoying because I know nobody else has gotten it, here. It's just me. For some reason. I'm just a tick magnet somehow. But anyway, okay, so till the next time and such and so forth and whatnot. I just have to find the right window to close. This is the one. All right, so thanks. And till the next time, and such, and so forth, and whatnot.